So now that we know what the shape is of the molecule, we can work out whether the molecule is polar or not. So when you write in it as polar, you'll write the positive end with a Greek letter delta, delta positive. So you just sort of do something like that and do something like that. And then you also write this dipole moment if it is polar. So that looks like a plus. And so the electrons are going over to this side. So that's how you know how to write it, which direction to write it in. And so just a reminder that the electronegativity difference, if it's less than 0.4, it's non-polar covalent. If it's greater than 1.8, it's ionic. If it's between 0.4 and 1.8, it's polar. So you have to find these two, H and F. And so you've got H and F. So H is over there, 2.2. So 4 minus 2.2 gives you very close to being ionic. So 1.8, it's on the borderline, unfortunately. And so this is the most electronegative element, and cesium is the least electronegative element. So a lot of these elements here where they smash together for like a fraction of a millisecond, or francium, there's only 30 grams of it on the entire planet, one of the last elements to be discovered, sort of don't count a lot of these elements that are on the periodic table. So francium just gets ignored because you'll never see it. So it may as well not exist for our purposes. All right. And so that is how you work out the electronegativity difference. And that's how you write it. Now, moving on from there, it must have, just because it's polar doesn't mean it's a polar molecule. So here we've got very polar bonds, C and O. So 2.6, 3.4, 2.6, 3.4. You're going to have to do this. So that's a difference of 0.8, so that is between 0.4 and 1.8. Once you've done these a lot, you get lazy and you sort of like, no, that's polar. Basically, if they're different, they're usually polar. You're going to see C and H quite a lot, and that's a difference of, that's borderline as well, unfortunately. That's 0.4 considered non-polar. And then you'll see that one quite a lot because of organics. And so you can see here, there's a negative area. I don't know whether there's much access, how much access there is to that. There would be quite a bit actually, because there's a concentration there's a double bond. But it's not a polar molecule in itself because both ends here are negative. Okay, so the crux is, I've deleted the word symmetry. And I've noticed the textbooks seem to have gotten rid of it as well, because there's radial symmetry and axial symmetry. Symmetry is not a good word. The correct physics word is net dipole moment. So I'm going to stick with that. There has to be a positive and negative end, basically, or it's not polar. It doesn't matter if there's positive and negative parts to it. There has to be an actual negative end and a positive end, not like carbon monoxide that we saw. Okay, so I think net dipole moment is the most precise and best word to use to say if it's polar or not. Okay, so you can't have bonds spread around it, not creating a positive or negative end. So if you have a look here, there's a pos and neg end there. There's a pos and neg end here. So there's the neg end. This one has a negative end, and these two here have polar bonds, but they're all spread around. So it might be positive in the center that you'd never see, and the whole thing's negative around the outside. And this one here, it is quite a small molecule, so there'd probably be steric hindrance and no access to the positive center as well. But that's not the point. There's not a positive and negative end. Okay, so that one is also considered non-polar. Okay, so that's how you do it. You have to look for a net dipole moment.